Thank you, everybody. So, some of you may have heard my other talks. Today I will be talking about hybrid rocket engines. And this is a very special kind of engine, and we have been working very intensely on this kind of engines because of its inherent features. So, we'll first give a short introduction to the technology, then I will talk again about propulsion basics, so that you get the picture, and then we talk a bit about internal ballistics of hybrid engines, what's a special feature of these engines, and then I will talk about some design we have made, and lastly we'll show some results. So, hybrid rocket engines. What are the applications? Well, when it can be used as a main engine or booster for launch, there was a company named AMROC that developed in the 90s a working launch system. Sadly, it went bankrupt, so we never saw it flying. But in principle, this is a proven technology and could be used for space launch. So it could be used for upper stage, for orbit insertion. And it is often used as gas generators, so to start another engine or to pressurize tanks, and sometimes even as an extinguisher. And very important today in the military or for amateurs, for unmanned aerial vehicles, it is used as a sustainer engine for drones because it has very long burn time and you can throttle the engine. So let's have a look at a principal schematic of such a hybrid rocket engine. So this part is the burning chamber containing the fuel that we call grain. Then we have the nozzle. This is the part that accelerates the heated gas. I will talk about this later. Then on this side, the liquid comes in. Normally, it's the oxidizer. There have been a design that's called an inverse hybrid, where the injected fuel, the injected liquid was the fuel, and the oxidizer was the grain, ammonium nitrate, and I think it was, I don't know, gasoline or something like that. So the main part of the hybrid rocket system is the burning chamber. Then there's a valve. The valve has to work at cryogenic temperatures if you are using cryogenic fluid, so this is the difficult part. If anybody remembers, Copenhagen suborbitals launched their Heat 1X this summer, and last summer they tried, and this was the main problem last summer. The previous summer that the valve didn't open because it was frozen. So this happened to us too. Then we have the oxidizer container. That's normally a fluid like, we'll talk about this later, liquid oxygen or something like that, and then we have the pressurant. So if we build an engine, we have to feed the liquid into the burning chamber at a certain pressure. Normally the higher the better. The problem is, of course, that you have to somehow put pressure on this liquid, and there are two ways to do that. You can use a pump, or you can pressurize it by a gas. So this is the main principle. This is very simple. So if you use a pump, the pump assembly would be here, and it would be the most complex thing, so amateurs normally tend to use normal pressurization by gas. Okay, that's the principle. So what are the pros of this design? There are many pros. First, it's inherently safe. That's something really nice. So hybrid rocket engines cannot explode by itself, like, for example, solid engines, and they don't do hard starts like liquid engines, and they don't burn up in flames and devastate everything, your test stand, and even people, if you use the right oxidizer. There was an accident with, what's the name, scaled composites, where they used nitrous oxide, and this is a monopropellant, and they did something wrong. There was some cavitation and it exploded, and I think 2 or 3 people died. But normally, hybrids are very safe. So, it's environmentally clean if you don't add any strange metals like beryllium or something like that to the mix. It's a proven technology. So, as I said, there were applications trying to make a launcher, and it was working. And it has been researched since the 1930s, so it's nothing new. The grain is very robust, so it doesn't matter if there are cracks or bubbles or something inside, like for a solid rocket engine, we have to take very much care about looking at the structure of the grain, let's say with X-ray or so. This is totally, it doesn't matter. In hybrid engines, grain could have bubbles or cracks or so, it doesn't even matter. So that's the feature why it's inherently safe. It has medium ISP, so between 150 and 300, you can a little bit go beyond that limit, but you have to use very exotic oxidizers and fuels. It has easy throttling. You have only to throttle one liquid. As in the case of bipropellants, you have to throttle. If you want to throttle, then you have to change 2 liquid streams. It's much more complicated than just one. You can shut down and restart the engines. It's very easy to do, as for example, compared to solid engines that are very difficult to restart and shut down. And it has reduced complexity and low cost as compared to bipropellant engines because, of course, the feed system has only to transport one liquid, and you don't have some mixing aggregators has to mix the 2 propellants. So, and another feature is it has a very long duration burn, and that's why it's used in test drones in the military and for UAVs. You can burn for 20 minutes or so if you want to, or longer. So there are, of course, some drawbacks. If these drawbacks weren't there, they would be using hybrid engines now. But they don't. So why don't they use it? Well, there's one problem, low regression rate, that in turn brings a very long duration burns. But if you don't want that, if you want a very short burning time, so a lot of thrust, then you have a problem. But you can counteract it. One way to counteract this is to use multiports. And the second way to counteract it is to use special fuels that have a very high regression rate because they have low viscosity when they melt, like paraffin. So there are additional effects that transport the fuel into the burning chamber. It has low bulk density. That means that a hybrid rocket engine is normally very large. You cannot build like bipropellants, very small engines, maybe just that small. So they are always 1-2 meters long because they need the mixing time. That's due to the process of burning. And they have normally a low combustion efficiency, so a few percent below of bipropellants and but they are better than solid rocket engines. So to improve the efficiency, you have to add certain mixing elements like diaphragms or so. So to make something like an afterburning by producing vorticity. And this, of course, adds additional weight to the system, so you have to build it bigger. And another problem is the shifting OF ratio. That is a ratio between oxidizer and fuel, because, of course, as the port increases in size, everything changes. The working point of the engine changes, and you have to counteract it by controlling. But today's electronic, this shouldn't be a problem. So there are some contrasts, and they are mainly used against the hybrids. So that's the real reason why they are under use is to these 4 points. So if you want to make a running system, you have to address these 4 points. So let's look at the fuels, what is used normally. So normally you can use any polymer, but one of the first, when they were available, was just rubber, polybutadiene. And then again, today is mostly used as HTTB, hydroxy-terminated polybutadiene, which is just a more viscous, more faster burning rubber. But you could just as well use polyethylene. We use that too. Amateurs like to use that. The problem with polyethylene is that when it melts, it expands, so it deforms and everything. Then you could, of course, use polypropylene, which is nearly the same. What's very nice is to use PMMA, polymethyl methacrylate, which is transparent, so you can watch the burn while it's working, and you can estimate, for example, parameters in the burning chamber just by optical inspection. Then what we used was polyurethane, nasty stuff, but very easy to process. Then some amateurs use PVC, polyvinyl chloride, which is really nasty because it produces chlorine exhaust, but is readily available in every hardware store. So, and then again, very, very good propellant that some guys in our group investigated too is paraffin, or what you can use too, very long alkanes, asphalt, for example. And this is a very high regression rate, so you can get to very high thrust even using one port, reducing the complexity of the engine. And very exotic fuel is pure lithium. So there was a program in the 60s, beginning of the 70s, where they used a pure lithium grain together with flux, and it achieved, I think, a vacuum ISP of 380, so nearly of a bipropellant, a good bipropellant. So oxidizer, what is normally used? Well, we used liquid oxygen, and it's, in my opinion, the best oxidizer there is in the world. But there are other opinions. So you can use gaseous oxygen. Of course, this is only for test stands because the density is too low for the engine to work in a real application. Most of the amateurs use nitrous oxide. As I said before, nitrous oxide is a monopropellant, so you have to be very careful about your injector design, about the feed system, not to make anything the way that a cavitation could occur, because this stuff can blow up with no notice, just blow up. Then there is a very interesting substance called red fuming nitric acid that you can only use with a bunny suit, no? Moon suit. Otherwise, you get burned. You have to use a gas mask. But otherwise, it is a very benign substance. So it doesn't explode by itself. It just burns everything in contact. And this one produces nitrous gases, so it's red fuming. It looks like directly coming from hell. And this one is not so dangerous in the sense that it doesn't produce so much fumes, but this thing corrodes everything. So you put it in anything that's not specially suited, like with Teflon or so, and it will corrode everything. So hydrogen peroxide is a very interesting oxidator, true. The problem with hydrogen peroxide is that it has a lower specific impulse because it produces water in the process. But it is very, very nice as a monopropellant. And there are guys that use hydrogen peroxide for hybrids. Then there is dinitrogen tetroxide. This is normally used for military applications. It's a storable compound. It's a liquid gas, like nitrous oxide. It's very similar. It's just adding two atoms together. And it's what makes the red fuming nitric acid red, essentially. So then we have liquid fluor, which is something very, very, very nasty, and you don't want to work with it, but they did. And even worse, liquid fluor plus oxygen called flux. And as I told you, this flux was used with lithium to produce a hybrid engine that went at about 380 seconds in the 1970s. So there are surely a lot of other oxidizers, but these are the best. Then as pressurant, there's not so much choice. Normally you can use just air, compressed air. The problem is that compressed air contains oxygen. And oxygen, if you let it flow through a feed line, then there is some inhomogeneity, some crack or something like that, and you can have an adiabatic shock. At that point, it heats up and it just ignites, and then you have a nice burning facility. So it's better to use nitrogen. It's totally inert. It's very cheap. The problem is if you work with cryogenic oxidators like with LOX, then of course the nitrogen will go to the liquid phase, so you have to put a lot of nitrogen in it. Then you could use helium, which is normally the best choice. The problem with helium is it's very expensive, and it goes through everything, so you cannot store it for a long time. And you should just buy it and use it up in a short cycle, otherwise maybe only half of the helium you buy it. So, and what's very interesting, there are people that use helium together with oxyhydrogen. Okay, oxyhydrogen as a pressurant is somehow crazy, yes? But there are guys in Switzerland, SPL, and they just take oxyhydrogen in a concentration that isn't explosive, so very low concentration, and then they take the helium and expand it through a catalysator with the oxyhydrogen, so this reaction takes place, produces water and a lot of heat, so the helium is heated and you need less helium than just pressurizing it with room temperature helium. Okay, so let's talk about the grains. Normally you just use a circular port. This is the simplest port, just a hole, and it's like an inverse flame inside, like a candle, but burning from inside instead of using some string. And then this is the double port design, typical, so the double D. So if you want to have higher thrust, you have to add ports. Of course, this makes the injector more complicated. And then the 4-port, and of course, the so-called wagon wheel. This was the design AMROC used for their launching vehicle. The problem with these wagon wheels is when they burn up, of course, these regions, these hollow regions expand until they touch. And then you are left with a web. And at this point, you have to shut off the engine. Otherwise, the web itself will start to deteriorate, to burn up. And then small pieces will go to your your nozzle at a speed of approximately Mach 1, so 1,000 meters per second or so, and will destroy the throat of the nozzle, thereby changing the flow, changing the working point, everything, and then deviating the rocket. So this is not a nice thing to try. Yeah, so these are the problems you have if you use fuel webs for multi-ports. So now let's talk a little bit about propulsion basics. This is very basic stuff, and some of you may have heard it already. When we look at a rocket, what we really use every time is the so-called conservation of linear momentum. Yeah? So for an inertial observer looking at some system where no external forces are working, this system has a constant momentum. So if you look at a rocket in flight, let's say with the velocity v, and we have here two masses, the mass of the rocket and some small mass delta m that is ejected in a short time frame delta t, then the impulse before the ejection and after the ejection, the momentum has to be equal. So you can write down a little equation. So on the left side, you have the momentum before the ejection, and on the right side, the momentum after the ejection. And if you look at it rightly, you just get to this little equation. You divide it by the time needed, delta t, and then you integrate it. So on the right side, we have just the derivative of time of velocity. Integrating it gives us the difference in velocity between the start and the end of the burn. And here we have something more difficult. This is the so-called logarithmic derivation. So when integrated, we get a natural logarithm in front. And we arrive at the celebrated Tsiolkovsky formula, which is the most important formula for mission planning. Okay? So for every mission you want to accomplish, there's a certain change in velocity the rocket has to achieve to perform the mission, and that's called the delta V. So the delta V, as Tsiolkovsky found out in the 1800s, is proportional to the so-called effective exhaust velocity. So this is the velocity that you propel the fuel, the burn gases, out of the rocket, behind you, of course. And then there is a logarithm, naturalis, of the mass ratio. So the idea is first to propel the exhaust gases as fast as possible away from the rocket, and the second thing is, at the end of the burn, to be as light as possible. So you get a very high mass ratio. Okay, let's look at delta V's if you're not very you don't know about delta V's. Where we want to go is to space. So we are on Earth, and the first thing to go is always low Earth orbit. And we need a lot of delta V to go to low Earth orbit, about 9 to 10 kilometers per second, okay? Knowing now that the effective exhaust velocity of rocket engines is in the order of, let's say, 2 to 4 kilometers per second, you have to achieve a very high mass ratio to get to this 10, okay? Once you are in low Earth orbit, you can see that all the numbers are much, much smaller. So, for example, if you want to go to the moon through a geotransfer orbit, you need 2.5 kilometers per second, and then again from GTO to a lunar orbit, 1.6. So in total, 4.1 kilometers per second. So the total way to the moon, the resting 380,000 kilometers, they only need less than half of the delta V you needed just to get to 150, 200 kilometers, okay? So this first step is always crucial. The rest is more easy to achieve. Once you are in lunar orbit, you can descend to the moon with 1.6 kilometers per second, which is very moderate. You can do it with a solid engine even. And then you can, if you want to go up from the moon, 1.6, and let's say we want to go to Mars, then we need about, again, I don't know, to this point here, about 3 kilometers per second, 4 kilometers per second. And the rest could be done by aerobraking. So to go from the moon to Mars, about 1/3 cheaper than go from Earth just to low Earth orbit. So it would be logical to first build a moon base, construct here the spaceship, and then go to Mars. It would be much faster, and the ship could be much bigger and take much more with it. And of course, they're planning on it. The Chinese, hopefully. So this is the major idea they had. It's called staging, looking at these delta V's. You can calculate this just with very simple algebra, what you need from the masses of the planets and the moon. And if you look at your normal exhaust velocity, you see that normally you cannot reach the mass ratio necessary of about 100 or so to go to the moon. So it would be possible to build one-stage rockets to go to the moon. But by staging them, like in the Saturn V project, you can just effectively add the logarithms, and you get at least the mass ratio of the end configuration compared to the start configuration. So for example, for the Saturn V, the start configuration was in the order of over 3,000 tons. So M0 was about 3,000. And when it got to the moon, I think it was to 40 tons or so. So you have a mass ratio of about 100. And then you get enough delta V to get to the moon and even back. Okay, let's talk a little bit of thermodynamics. This is necessary because I want to show you some formulas that contain a lot of signs that are very difficult to understand if you not have seen them anywhere else. So there are two laws in thermodynamics. The first law is you can't win. And the second law is you shouldn't even try. So the first law is about the inner energy that can only change by adding heat to a system or work, or extracting it to reduce the inner energy. And the second law states there is some strange state variable called the entropy, and it's somehow connected to the heat flow at reversal process. Okay, so energy and temperature. You may have heard about Boltzmann constant. Everybody physicist knows about it. It's a very small number, 10 to the power of minus 23. And what it essentially says is, if you have a molecule or an atom at a certain temperature, let's say at 300 Kelvin, room temperature, then you can calculate with this constant the mean energy per degree of freedom. So degree of freedom means the way a molecule can move, let's say in direction of X or Y or Z, or it can rotate around an axis. So for example, for a diatomic molecule, you would have 5 degrees of freedom. So you could calculate that one single molecule would have in the mean 5/2 kBt. So then there's another notion, very important, heat capacity. This is just if you take any system, let's say this glass of water, and you want to improve its temperature, then you have to put some energy in it. And the heat capacity just says how many joule you have to put in to reach, to increase the temperature by 1 Kelvin. That's heat capacity. So if you do it by constant volume, like for example doing it in a cylinder, then it's the heat capacity constant volume. There's a very nice entity called enthalpy, which is just a Legendre transform of the inner energy, and this leads us to the heat capacity at constant pressure. So this is something that normally takes place in our environment. If you heat something, it always happens at ambient pressure, at air pressure, so it's a constant pressure. So what you normally measure is the heat capacity constant pressure. And there is something called the adiabatic index, gamma, or sometimes called kappa in the formulas, and it's just a ratio of these two heats. And it's a number that is close to 1, always a little bit higher, so between 1 and 1.666. So this is a number that is always used in rocketry equations. So don't be alarmed. It's a very simple number to understand. It's just some small number between 1 and 1.666 that describes the constituents of the gas that is exhausted. So also to some chemistry, molar and specific quantities. So there's the Avogadro's number, which is just the chemist's way of saying a dozen. Yes, a dozen is a small number, 12, and Avogadro's number is just a larger number, but it has to do with 12, because per definition, the Avogadro number is the number of atoms in the isotope C12 if you have 12 grams of it. Very funny. So this is the number, very, very high, and if you multiply our Boltzmann constant that has nearly the same order of magnitude, just in the reverse order, you get to a small number, about 8, and we call that the universal gas constant. So just remember, R is in the vicinity of 8. Then we have the amount of substance, just taking all the molecules, dividing it by this number, and you just, instead of saying I have 12 to the 10 to the power of 23, you say I have 2 moles. And just saying when you have 24 eggs, I have 2 dozen. Then you have the molecular weight, very important for the formulas that will come. It's just the weight that 1 mole of the substance has. So you take 1 molecule, look at its weight, and multiply it with Avogadro's number, and you get some number in the region of grams. So for example, water, which is made of oxygen and 2 hydrogen, would be 16 plus 2, has 18 grams per mole. So if you have 18 grams of water, there are about 6 times 10 to the power of 23 molecules in it. So we know the molar concentration. This is just how many moles in a liter. then the number concentration, how many molecules in a liter, the mass density, how many mass per liter, and the specific heat capacity is just taking the heat capacity of a system and dividing it by its mass. Okay. So then something very important, the so-called velocity of sound. And it's a very simple formula, and here we see for the first time the adiabatic index. And for example, if you want to calculate the velocity of sound here in air, then you have to put in the temperature that we have now, let's say around 300 Kelvin, then divide by the molar mass of air, I think it's in the order of 28 grams or so, and multiply it by gamma of air, which is in the order of 1.4, and multiply it with 8.314, and take the square root, and you get about 340 meters per second. Okay? So if the temperature rises, then the speed of sound rises too. So in a hot gas, the speed of sound is higher. If the molecules of the gas are heavier, then the speed of sound is lower because the molecules have to be pushed around and they are heavier, so they don't want to be pushed around. So if you take hydrogen, we'll have a very high velocity of sound, and if you take, like, for example, xenon, then it's very low. So for example, if someone breathes in helium, but it's very low, you can also, of course, take hydrogen, but it's very dangerous. So if you take helium, then you have a very same sound. Okay? They go up, they gain. And that's because of this velocity of sound. It changes. The velocity of sound in helium is much higher than in air. And if he breathes in xenon, then he gets a very low voice. Okay? Because the velocity of sound is so much lower. So, and then of course there's the celebrated Mach number that anyone knows. It's just dividing the velocity of the object you are looking at by the local sound velocity. Okay, let's talk about the ideal gas. I have a nice metaphor for it. Just imagine that you have N hooligans, okay? And they are confined to a space V, and you make them angry with a temperature T. Then they will exert a pressure V on the environment. So you just can divide it by V, then you have the number density of the hooligans, or you can divide it by Avogadro's number, then you have something that chemics like with the molarity, or divide by V, then you have the concentration, the molar concentration. And what is normally used in rocketry is this equation. So if you come around this equation, it's always ideal gas, all the same. Yes, this is, in this case, it's the density rho. And the molecular weight m is now introduced. So, what are the properties of ideal gases? Well, we can calculate the adiabatic index because it's just given by the number of degrees of freedom plus 2 divided by the number of degrees of freedom. So if we have, for example, a diatomic gas, like in air, nitrogen and oxygen mostly, then the number of degrees of freedom is 5. 3 for the translation and 2 for rotation. So 5 plus 2 is 7, divided by 5 is 1.4. Okay? It's that easy for an ideal gas. Then the difference between the two heats at constant pressure and constant volume is just R, also 8.314. And you can even directly calculate Cp. That's very important because if we do gas expansion, what we're interested in with the nozzle, then we can simplify things and then get exact analytical expressions that we can just calculate and then get the properties of the engine. So the simplifying assumptions are one-dimension flow, steady flow, no change over time, adiabatic, no flow of heat, isentropic, and ideal gas, of course. It's done only volume work, so the gas expands and works against the environment, and no significant changes in potential energy because our engines are normally so small that they are negligible. So if you do that, then you get one constant of the motion of the gas, and it's called the stagnation enthalpy. What you have to know is just that it is constant, and it changes with the speed that the fluid travels. So if you are at the stagnation point, this red point is an airfoil, so the flow stopped here, okay? And everywhere else, when the speed gets up, then the enthalpy goes down according to this law. And interestingly enough, for an ideal gas, you can calculate the enthalpy by just multiplying the absolute temperature with this heat capacity at constant pressure. And we have seen that we can calculate this. So this is an interesting formula because you can calculate the temperature T0 at the stagnation point, knowing the temperature around it, the ambient temperature, for example, 300 Kelvin here, and the velocity that the air is streaming. So if you have, for example, a foil, you could calculate the temperature at the stagnation point. Or more interesting, for rockets, you can calculate the temperature at the tip of the rocket. You can see if V gets very high up, so let's say Mach 3 or so, or higher, and its temperature goes beyond 500 Kelvin, 600, 700 Kelvin, 800 Kelvin, so you cannot build tips out, for example, of aluminum. It will just melt away, okay? So with this formula, you can calculate this, and you can calculate all the formulas I will show you now. So this is the basis for all the formulas for one-dimensional flow in rocket engines. So now, to the so-called de Laval nozzle, the convergent-divergent nozzle. This is the one piece of engineering that produces the most power on Earth. With this simple device, every normal power plant produces electricity, okay? So by expanding hot steam to very high speeds, you turn the turbine and then you produce electricity. And of course, it is used in rockets. And as you may know, rockets are the most sophisticated and most powerful engines ever built. So, what happens is that hot gas enters the convergent section, then it speeds up, and exactly at the throat it reaches Mach 1, so local velocity of sound. And after exiting the throat region, it even accelerates more and achieves hypersonic sound velocity, so maybe Mach 4 or 5 or so. And you have the effective acceleration of the gas. So the thrust itself is now calculated from two terms. The first term, m point VE, is the outflow, the rate at which momentum is exchanged by pushing away the mass, the propellant, the gases. And the second term is due to the ambient pressure and the pressure at the exit of the nozzle. So that's the difference, delta P, times the area of the exit of the nozzle. So this is an additional term that cannot be omitted. And this term effectively changes the velocity of the gas from the exit to infinity. It may decelerate it or accelerate it depending on the pressures. So if the pressure, the ambient pressure is higher than the exit, nozzle exit pressure, what is normally the case at ground when you are testing, then the gases will be decelerated because they have to work against the ambient pressure. But if you are in space in vacuum, then they will accelerate by the atoms pushing it forward, in a sense, without any nozzle wands to lead them. So then you can, from this, just by dividing by m point, you can calculate the effective exhaust velocity that we had in our Tsiolkovsky equation. So very importantly, with this effective exhaust velocity, you can calculate the specific impulse of the engine, the one number that defines how efficient the engine can accelerate the gas. And it's measured in seconds, and it's normally in a range between 100 and 450 for the best engines. So this is actually an equation from the 1700, I don't know, very old, or no, 1850 or so. And it just describes the exit velocity depending on the stagnation temperature, the molecular weight of the gas, universal gas constant here, the adiabatic index. This is the pressure in the chamber, and this is the exit pressure at the nozzle. And if you just enter everything, you get the velocity at the exit of the nozzle. And if you look at this formula, you see that it's proportional to the local speed of sound in the burning chamber. So the higher the speed of sound in the burning chamber, the better. So if you enter everything and you get this nice equation, I don't go into the details. This is just a thrust equation. You just take this formula, put everything in, and you have an estimation of what the thrust of your engine will be. And this is important, as we will see soon, that you know what the thrust is before testing. Okay, let's talk a little bit about hybrid combustion. The main feature of hybrids is the so-called diffusion flame. So in solid fuel engines, the two propellants, the oxidizer and the fuel, are mixed so intimately that they directly react at the burning front. So there is normally not much reaction in the gas phase except if we have metals. In the bipropellant, you mix the two propellants by impinging them or something like that, and then they burn up in little droplets in flight. So in a hybrid combustion, you have a diffusion flame, and it means that the fuel is gasified during the reaction. And you have turbulent mixing between the two layers. This is fuel-rich, this is oxidizer-rich, and this is the flame front. So you have mixing between them. You have here blowing away from the wall. And this here, due to the very high velocity of the oxidizer, you have normally a very high Reynolds number, so it's a turbulent flow, hopefully. So the reaction takes place in a very small layer, the flame layer, where the two have the correct stoichiometric ratios. And it's nature's way of burning things. So if you look at the candle, you are looking at a diffusion flame. Okay? It's just the same thing in principle. So now to the burning rate, which is the dominating parameter to estimate the thrust. So you have heat flowing from the flame front down to the fuel, and we call it here dot Q for the wall. This is the heat that flows into the wall from the flame. And on the right side of the equation, we have the amount of fuel that evaporates per second times its enthalpy of evaporation. So there's a certain kind of energy needed to transfer the fuel from the solid phase to a gaseous phase, or mainly first to a liquid phase and then to a gaseous phase. And this is the main feature why hybrids are inherently safe. Because if something goes wrong, if anything goes wrong, then normally the pressure in the chamber drops, the flame goes out, and no more propellant will be evaporated. And there is no intimate mixing of oxidizer and propellant possible, like for example in bipropellant engines, when there is some fault and these two things get together, like for example kerosene or LOX or hydrogen or LOX, then there's a very nice fireball, but only from the far, okay? So you're standing near to it, that's it. But with hybrid engines, they may blow up, but then it's over. There will be no explosion. So the heat transfer is calculated by this equation, and it's very complicated. I won't go into the details. You have to look at the Bernoulli boundary later, gas conductivity, the temperature distribution across the burning chamber. You have to know the specific enthalpy of the gas, so you have to do some thermochemistry to know what the combustion looks like. And of course, you need the specific heat of these burning gases. So when you do all that, then you get at this equation that describes how the burn rate goes. So R dot is the amount of length that the grain loses per second, so some millimeters per second. And it is calculated by a power law. And this power law contains a regression coefficient. G is the total propellant mass flux rate along the port, and X is the distance along the port. So you need two exponents, n and m, and they're on the order of 0.8 for n and minus 0.2 for m. Okay, and then of course you can simulate it, and you just initialize simulation and calculate the regression rate with this formula. Then you calculate the mass flow rate by knowing how much oxidizer and fuel is now in the burning chamber. Then you calculate the temperature using thermochemistry. And you calculate from that the change in the chamber, nozzle, and engine performance. And upgrade, of course, the grain is slightly changing, the port diameter is increasing, and the nozzle may be increasing too, but because there's ablation. And if not all fuel has been spent, you just start over too, and you repeat it until you have done the simulation. So that's how a simulation of a hybrid motor, rocket motor is done. So I will now talk a little bit about the design of our designs we do, especially on the so-called advanced lithogold propulsion hybrid aggregate we worked on. This is a draw of it, and it had a graphite nozzle, and it was totally decomposable. Side view, view to the nozzle. This is the injector part, and this is the decomposition. So we wanted to make it modulary, so to change everything between the tests. And this is the inner view. It's not very good visible. The contrast is very bad. So here's an aft-burning chamber, but you can't see anything. It's a problem, sorry about that. Okay, this is the tank section we have envisioned. It's still not working, so you have here the dewar. And from the dewar you put the logs into 4 tanks, and these tanks are then heated by hot water, for example. And then we have several valves and pressurization valves. And here's the real hybrid engine. So this is a view of the 4 tanks. Here these are made of aluminum, and you have copper how it's called, tubes that will transport the hot water to boil the oxygen. And this is a view with all the sensors integrated in this tank assembly. So of course we did some additional design. This is a vision. We never worked on that. But this would increase the bulk density, so you could make more compact hybrid engines, and we call it the Onion. It's basically a torus with an aerospike. So the liquid oxygen or whatever oxygen you choose to use just goes down first to the aerospike, cools the aerospike, and then is injected as a liquid into the torus and circulating around. So this is how it would look like. You would have a tank assembly above, and then it would just go with a valve through here, then eject here, and there would be a burn. Okay, this is a close-up of the aerospike, and it will be during burn. So we have here very nice vorticity that would increase burning efficiency, hopefully. We don't know. We didn't test it anyway. It would increase the combustion efficiency. And this is a possible way to make a smaller engine and to inspect the burning before building a really large engine, because this engine you have just seen would have, I don't know, about 80 kilograms of fuel and would spend over 300 kilograms of logs at once. So, now I want you, before I end this session, I want you to show you some videos of some tests we made. Okay, videos. So at first, okay. Nice. It's not working very well. Do you have any sound? Wait a second. I will open it with another one. So. Sorry about the delay. Yeah, it's difficult, I know. Yeah. Okay. One second. I will make full screen. So this is a typical assembly we do. So this bubble here is the LOX tank, and then you have the valve below here. And this is the tanking, for tanking, and this is the engine. It all has started. So we'll see how it goes. Thank you. Okay, but you haven't seen anything. Wait a moment. So this is a typical scenario when something goes wrong with a hybrid. It blows up, but then it stops. Okay, then it's over. And that is why we had this shield there. We had anticipated that we would have problems because one test before something similar happened, but not that brutal. And there was another test that was not so bad. Went quite smoothly. We used for the second time a graphite nozzle, but our injection system failed again, but in another way, as you will now see. So the logs just burned a hole through the hull, and then in the moment the pressure went out of the chamber, the reaction stops and everything is safe. So let's see at this test here. This is my favorite. This is my favorite. You have to hear the birds before it starts. Very nice, very peaceful. It was 10 years ago. So this is why you really should look at the formulas and calculate the thrust before you do some work, okay? What happened was the engineer that designed this thing, he had a very great idea to injecting the logs through a rod, through a tube, but unluckily it burst open and then, well, let's say the engine just improved its performance, okay? So, but of course we had working tests, and I want to show you this from 2004. And this is very, how it's called, langweilig, because it works all the time. Okay, let's see. Okay. So this was our last successful test we made in 2004. Since then we went to solid rocket engines. As you can see at the end of the burn, it gets somehow unstable. That is because all the liquid is spent and now it's running on gaseous oxygen. And the pressure goes down very fast. So the burning is not so stable, and that's why it starts to chuff and so. Okay, so I think that's all for today. I hope you enjoyed, and I hope to see you soon on our homepage so you can see our progress. Thank you for your attention.
So, are there any questions? If yes, please come to the front and pose the questions. Okay.
How do you ignite the hybrid engines, and can you do it several times? Like, can you turn on and off the machine? And
yes, our design was focused on making the injector work, because we tried to make an injector that improved the turbulence inside the burning chamber without adding additional mass, so without adding a diaphragm. So we didn't concentrate so much on the igniter. We just used some pyrotechnic device that first started. I can show you in one of the movies. So there are groups that did propane gas burners to make it restart able. And I don't know what they did, but it was successful. So at this point, the pyrotechnic has ignited, and there's some oxygen flowing from the tank through the hybrid, because the valve wasn't exactly sealed, and it was to our advantage, because then the hybrid engine is really hot and warm when the main LOX comes in. And as you may notice, above the LOX tank there is a small puff, and this is a device to increase energy input to the LOX tank, so the pressure doesn't go down so fast. Okay, but this has nothing to do with ignition process. So we just fired it once and just let it burn. So we didn't do reignition, but it would be possible in principle.
Okay, second question.
Yes, I would like to know how well these rockets scale. I guess your aim is space, so and what we've seen so far is quite small rockets.
Yes, yes, you are totally right. These rockets, well, this one developed a thrust of 160 kilopond plus when it toppled over, but the other rockets about between 40 and 60 kilopond. So they were not really big engines. The problem with hybrid rocket engines is that they don't scale so good. This is due to the scaling in the hydrodynamics with Reynolds number and so on. You really have to take the real size to get it running. So you have to really build a big engine and then test it on a big engine. You cannot build a small engine and then hope that it will be the same as in a big engine. That's true. So we will be going in the next years, I hope, to larger engines. Now we have the possibilities to do that. And we will see. We have working designs from AMROC, really large. So we know what to do in principle, but we have to test, of course. No other way.
Okay, second question. What is the status of the Alpha rocket?
At the moment, it's dormant. No, we have made the design in 2004 and 2005. And when we decided to first go to flight, here's the rocket. And the problem was that the hybrid rocket engines were at the moment too complicated to terminate. And we worked at a time on a hybrid rocket called Hera from a colleague, but he just abandoned the project. And since then we have only used solid rocket engines because it's just simpler to do, just to go up in the air. Yeah? The problem is if you just want to go up, let's say 10 kilometers, like we can do with the Arguna 4, then the hybrid rocket engine has absolutely no advantage. No advantage. It has the advantage when you really want to go into space that is 100 kilometers plus. Okay? So for low altitude flights, it is not really an alternative, except if you're making UAVs. Okay?
So are there questions left? Okay, so we learned today how to build safe rockets. Also, I wouldn't tag it with safe for trying it at home. So thank you very much for this presentation. Give him a warm applause.